Good afternoon, everybody. So nice to see you here on a Friday afternoon, right after lunch. I hope you're not too groggy. Okay, let me just take a quick poll before getting started. Show of hands. Who has fallen asleep? Oh, okay. All right. Thank you for being honest. I do hope I can wake you up, or at least prevent everybody else from falling asleep today. Because I'm going to be talking about the tools and techniques that we at ING have made available for teams to use in order to improve the way how they work and improve the way how services and APIs specifically are built. This is probably not new for many of you, but it is nevertheless a case study. Now, before we get into that, anyway, small story. Years ago, or let's be honest, decades ago, when I was at the beginning of my own professional career, I was working at a tech company established, surprisingly enough, in a small fisherman's village in Portugal, not too far away from Lisbon. And what we did back then was something that became increasingly popular over the years. We were building desktop applications for companies that needed to identify persons and goods. Now, in other words, what this means is that these desktop applications had to interface with hardware, physical stuff, plastic card printers, label printers, chip card readers, magnetic stripe encoders. These were, back then, still very much a big thing. In most recent years, contactless chip card encoders. And had to coordinate all these moving parts in order to print a card or encode a label that was going to be pasted on some box somewhere. The challenge back then was to ensure that all components were working seamlessly. Now, how would it work when we had to support a new printer? Someone would give a call. The manufacturer usually would say, hey, we would really like you to support this new printer. We'd go, sure, ship it over. Comes a box, a printer, we connect the cables, we look at the manuals, we implement something, and guess what? It doesn't work. Then back and forth would start. My point here is that things have a tendency, and it does not matter if it was over 20 years ago or if it was yesterday, when different components are at stake, things have a tendency to not work on the first try. Now, there are many causes for this, and this leads us to the first lesson that anyone working in software and systems learns very quickly. 100% reliability is a holy grail. It's not going to happen. And that's why any service provider worth their salt measures availability in terms of nines. They can go to 99.999%, but no one ever dares to round that up to 100 because it's not going to happen. Now, we can get close, indeed. We can get close. 99.999% is already pretty good. But why on earth is 100% impossible? Because systems in general are extremely heterogeneous. I always have a problem pronouncing this. There are too many moving parts. If we just look at the way how data centers are built, the very first thing that can fail is the network. Their packets can be lost. Interfaces may be wrong. Communications fail. Even something as simple as crossing the street can fail. Come on, I'm based in Amsterdam, and when trying to cross the street in the middle of the city, it's very likely that I run the risk of being run over by a delivery person. And from what I've seen in the past few days in London, that's also the case. Network failures, crash failures, protocol failures. There's even a special word to Byzantine failures. It basically means that anything can happen. We need to focus on one problem at a time. It's just humanly possible to cover everything. What did we decide to cover first? The aspect of systems building that, strangely enough, is something that we all, each and every one of us, have direct control over, which is human communications. Now, every time someone wants to build a new system, a new API, well, that service is not going to work in isolation. It's going to connect to something else, and that something else is usually managed by another team, another set of people. And these people need to talk to each other. Generally speaking, these happen over a cup of coffee, over a few emails, in a chat box. And over these channels, it is extremely easy to miscommunicate something, because the person delivering the message assumes that the other knows as much as the system as they do, which is often not the case, or just because they forgot something. The idea is to make everything that is implicit explicit. This is borrowed from domain-driven design, by the way. And to ensure that machines have means of validating what the humans want to do. Therefore, for the remaining of this session, I would like to face this problem as if we were looking at an application, at some code. And as you know, when we build an application, we go through different stages. And the first stage in any application is to compile our code into bytecode, machine code, whatever. You may wonder, how on earth does that apply to a service or to an API? Well, it is a matter of opinion, of course, but can we represent an interface as code? Well, yes. One way of doing that is ensuring that we have a standard format for specifications, for example, Swagger, or generally speaking, OpenAPI, that people can create, and then we can take those specifications and convert them into code. You see on screen the Java logo because, well, ING is mostly a JVM shop, and therefore many teams use Java. But this is the first step. What are the advantages of opting for an approach where we first design the API, an API-first development approach? Well, first of all, the specifications are text. And by being text, they can easily fit into the normal source code control system and review processes you have in place. You can do peer review on that. Easy. Team members, when getting together to refine something, they can immediately edit that text. Another advantage that sometimes is a bit overlooked is that by using the appropriate converters, we can even use those specifications, transform them in such a way that, well, they may be extremely technical and share with some stakeholders, for example, that other team who wants to consume your service, or we can convert them in a more simplified way, which supports conversations with, for example, business stakeholders, because they often want to know precisely which data is coming in and out of your service. And then, of course, code generation itself, which then gives you a runnable artifact that flows through your continuous integration and continuous deployment pipelines. All of this builds a feedback loop. People get together, they design an API, they write the text, and when they are happy with the text, they generate the code for the service. As I mentioned before, we are mostly a JVM shop. Lots of our teams use Maven. And we have chosen the OpenAPI plugin to transform the specification into a runnable service. Now, the advantage of doing this at this point is that even if we are only in the prototyping stage, we already have an artifact that can be deployed, can run, and is already serving requests. It can either serve some static demo sample data, or it can return a non-implemented response. Now it's up to the team to decide that. But even at this stage, you can already get a running service. Then you get busy with implementing things, the actual business, the actual value. By the time you are done, you can validate the implementation by using tools such as Wrestler or Schemathesis to ensure that your implementation respects the letter of the specification. And these are not functional tests, by the way. These are only validations to make sure that whatever you did not step outside of the specification. This is especially useful for testing the validity of whatever it is that your service is returning. You deploy. You wish you could go have a beer or something for the next 6 months, but of course change is inevitable and everything starts and repeats itself again. To summarize our API first development process, we strongly recommend teams to build the OpenAPI file first and make it as detailed as possible, because the interface code is going to be generated from it. Once the code is generated, then it can be extended with the real business code. Now, one thing that used to happen in the past was that people would forget to change the specification. Now, people would go to the code, they would decide that some new attribute had to be added, or worse, an attribute had to be removed. They would change the code, publish it, running, and then someone would call in, send an email, whatever. Hey, what's happening? Oh, yes, we forgot to change the specification, and people did not know about this. By editing the specification first, then we can be assured that whatever it is that's being built respects it to the letter. Now, we have an artifact. We compiled our specification into code. Everybody's happy. Next stage. Right now, the code generated from the specification works kind of as intermediate code, byte level code, the kind of a parallel. We still need a couple more steps. And we need to not only transform that into deployable artifact, concept-wise, but here at the assembly stage, we need to ensure that the artifact we are producing can work together in a system. We need to verify that they work together. And how have we chosen to do that? Well, we strongly advocate the usage of contract testing, pact in this case, which is pretty much as in a coffee shop. When we go and we order a coffee, we look at the person the other side of the counter, we ask for black coffee, for example, and you expect a black coffee in return. You don't expect a cappuccino. Otherwise, something went wrong. With contract testing, the logic is the same. The consumer writes tests that generate a contract file, which the provider service then needs to validate. Now, the idea is that not only the consumer uses that contract to test its own code in order to ensure that whatever it is that it is doing, it is respecting the contract, but also the provider needs to use that contract to make sure that whatever it is that it is serving respects what the consumers want. Now, that is what I call testing the spirit of the specification. We test the letter, and now we test the intention behind the specification. Additionally, we include a can I deploy gate that teams can use to ensure that in case there is a mistake, a test is failing, then the artifact does not get any further down the line. How does that work? We do use Azure DevOps. Therefore, when the consumer is being built, its pipeline is executed. A step in that pipeline uploads the contract into packed flow, and it will automatically trigger the provider pipelines. Those pipelines on the provider side are going to run tests against that contract. The test results are going to be uploaded to packed flow, and the consumer pipeline will then receive those results and will decide whether it can move forward or not. It does apply to both the consumer and the provider. If tests are failing, then it means that those two pieces of software are incompatible and they should not be moving forward into any deployment. Now, another advantage of this approach is that when tests fail at this stage, then it gets people talking. Teams need to communicate with one another. Some assumption has gone wrong and they actually need to talk. You know that difficult thing, which is step up and talk to someone. People really need to do so. Now, let's just assume for a moment that tests are green, everything is fine, artifacts are good. But at this point, what we have been testing has been running either on someone's computer or in a pipeline. None of these artifacts has been released into the real world yet. And that is what the linking stage is all about. We now actually connect the dots and see if they fit. To do so, unfortunately, means using real environments. In this case, a staging environment, or non-prod, if you prefer, because there are some things that we just cannot test in a computer or in a pipeline. Think about, we use OpenShift, so Kubernetes deployment files or Kubernetes secret files. In the actual environment, think about firewalls, think about connection URLs. That kind of things can only be validated on the actual environment. And teams also take this opportunity to run their performance tests, of course. And the recommendation is that at this point, then teams will run just a couple integration tests that exercise only the critical business process that their service is serving to ensure that everything is indeed connected and working together. The goal is to confirm that all the tests that were done during the build and deployment phase hold, and the runtime configuration is correct. And of course, this happens every time there's a new version. That's why it's called a continuous integration and deployment environment. Now, tests have passed in staging. Everybody's happy. Big smile on their faces. Time to offer the new feature to customers. Even though everybody has heard of Murphy's Law, right? Whatever can go wrong will go wrong in the possible worst moment ever. When deploying a service, when is the possible worst moment ever? When it reaches production, of course. Hence, another strategy that is strongly recommended for teams is a canary deployment. Now, I'm pretty sure all of you are familiar with the canary in the coal mine metaphor and the real poor thing canaries that were taken into the coal mines to warn the miners when the air was becoming too poisonous for them. We do the same thing with services. The current service versions are kept running. One or two are deployed. They get a small fraction of traffic. When everything goes right, then the old versions are replaced as the new version is scaled up. In the event that Murphy is right and something does go wrong, then the canary version can be quickly taken down, and hopefully either customers did not notice or just a handful were slightly inconvenienced by whatever it was that went wrong. When combining everything, we find that teams' confidence into the services that they are building is increased enormously. After all of these checks and balances are in place, we find that any integration problems that do appear are often non-trivial. It's not that small thing such as, oh yeah, you expected a floating point number, but we are sending only an integer, sorry about that, or the other way around. Whatever happens is usually harder to find out. And this is what we want. Well, we don't want hard problems, but we don't want to see problems reaching to production if they are as trivial as a simple data type mismatch. That's what I mean. Going back to 20 years ago, well, these techniques would not have helped back then because, as I said, I was developing desktop software connecting to actual hardware, so there was no pact for hardware back then. But if there was, I am pretty sure that I would have spent a lot more time in the company of those nice people down there by the beach than getting some new white hair trying to figure out some integration problem with a new printer that had came up. This is what we recommend, and I hope that I could have inspired you in seeing that, well, other companies do integrate these things and they do work. In the meantime, we do have a few minutes left, so if anyone has any questions, now it is the time to ask. If not, then those who nevertheless fell asleep can go and grab a cup of coffee. No? All right, then thank you so much.